So let us look at a simple IDE disk driver, which is basically an interface to the system. I have to note that I have deliberately cut a lot of information about HDD disks, how they are, and the sectors and the seek time, and how do you calculate this and how do you calculate that, for a reason, basically because this is almost becoming obsolete. HDDs are almost becoming obsolete. I also think that this is a better study in architecture course or a computer organization course, um, for multiple reasons. So I have cut a lot of this information. Nevertheless, I would highly encourage you to read that in the book, because they sort of give you some perspective on how things were done rather than how things they are or will be done probably by the time you graduate. Because right now SSDs are becoming cheap. They are very good. They are almost as reliable as HDDs, if not more reliable. Yeah, I have failed too many HDDs in my life. I've never failed an SSD in my life. While my sampling set from HDDs is much larger, but still, I mean, the technology is catching up so fast that I don't know if this statement is true, but I think SSDs are now actually as reliable, if not more reliable than HDDs. So this is very little information on how disk drives are, for that reason, basically. So let's get back to the interface part. So typical disk driver interface, and that is regardless in probably of its type. You'll have a control register, you have some command block registers, many of them, you have a status register, and you have an error register. And some of these might be memory mapped, and in that case they will have a definite IO address, and that or predefined IO address, and 0x3f6 for example might be one of these IO addresses for reading or writing to for some of these registers, or you can just use the in and out command on x86 to actually access these. A simple IDE disk driver protocol will look something like will be like this basically. You wait for the drive to be ready. Okay, you need to wait until you can actually write or read from the device, and then you read status register, which have some number, until the drive is ready and not busy, basically. And then you write parameters to the command register. Write basically how much data are you going to write. Okay, where should this data be written, and which drive should this data be written to, because you might have multiple disk drives, so you might have like 5 of them. And again, this is not really history, but this is sort of current technologies, that many of the HDDs that you find today, when I explain to you how they look like, you have like the magnetic tape and you have a needle on top. Right now, many of them are actually they are a tower. Okay, they form a tower. There are multiple discs on top of each other, multiple needles on top of each other, on top of each disk, sorry, and basically you have basically sort of multiple drives in the same even hard disk. So basically you write parameters to code the command register, saying if you're reading, writing, whatever. You start the IO process, okay, by issuing read or write to command register, write read or write in the command to command register. You start the data transfer, basically waiting until the status is ready, and DRQ, which is again yeah, another status, which is basically the drive request for data, and write data to the data port. So in this case you're writing basically, so the device is ready, it has done the seeking, it's now waiting to write whatever you're going to write, so it sends you a DRQ, drive request for data, and then you send it the data and it writes. You handle the interrupts if there are any interrupts, and you do all the error handling. Of course, This is not how things are today, because you have caching on top of these device drivers. You're not really, well, in even the most basic computers, you do not really do it that way, because you have the data, you have sort of a CPU on top of your hard disk that actually controls this whole protocol. But again, this is very very fast becoming obsolete, and I'm not really sure how important is it. But I wouldn't. I'm not. I'm not teaching it, but I think you should read it. Um, so most drivers have large number of sectors. Each of these sectors is 512 bytes. I actually said 512 kilobytes. I was wrong. It's 512 bytes. Each of which can be read or written, and this is exactly what I was talking about. And the sectors are numbered basically from 0 to n minus 1 on a disk with n sectors. So each you can have like 10,000 sectors on one disk or whatever. So this is what is used basically to address the different ports. So if you're writing to sector 1, you're going to write the first sector, then you're writing to sector 0. If you're writing to the last sector, then you're writing to sector n minus 1. And multi-sector operations are possible. Actually, most file systems would read 4 kilobytes at a time or more, because anything else is just like very slow. But then devices, I mean, again, I think this is historical information, so it's written in the book. But when updating the disk, since you have multi layers in the disk now, you can actually write more than 512 bytes in parallel atomically. But yeah, done with the disk drives part. I will not ask you about seek time and this stuff. So far we have talked about two key operating system abstractions: the process abstraction and the address space, the virtual address space. Okay, there is also a third abstraction for basically I/O, which is for persistent storage. Basically, it's virtualization over the storage subsystem. And the idea now is, how do we manage persistent storage in the operating system? What are the APIs and what are the important aspects of the implementation? As you all have been using computers, hopefully in the past 20 years, files and directories are the key to accessing any data on your computer. You have files and you have directories or folders, or call them, I mean, they have different names, but it's basically files and directories. And these are your two key abstractions. You, as Paul or Mark or Ahmed or whatever, you just know that to access my data, it's on a file, right? To read my CV, it's on a file. To read my exam, it's on a file, right? So the way that this is implemented is that a file has two properties. It's basically a linear array of bytes that can be read and written. So a file is typically, not always, but typically, you try to write a file on the same sector, for example, or consecutive sectors. In some cases, you might end up not doing that, but these are very rare cases. But anyways, you typically have a linear array of bytes that can be read and written. They are bytes that follow each other to the operating system, to the higher level, to the application basically, to the higher level of the operating system. What happens on the disk drives is something different. And you have so that's the first part of what the file is. The second is that it has a low level name, which is usually a number called an inode number. So each file, you have a file name, which is like a high level name. Okay, for example, bar.txt, this lecture.ppt, or ahmed.cv, ahmed underscore cv dot pdf. Okay, you have a higher level name. Okay, but for the operating system, each high level name is actually mapped to a low level name, which is usually just a number, and we call this number an inode number. Okay, in most operating systems, the operating system has no way to check if the file is in the format that you actually claim it is. So, for example, if I'm basically having a file that is, if I save this set of slides, these PPT slides, or I rename them to Ahmed underscore CV dot PDF. The operating system has no way for checking if this file is in PDF format. Okay, if I call it Ahmed underscore family dot PNG, like these slides that I'm using, again the operating system has no way of knowing if it's a picture or not. What would happen is that when I try opening it with like my photo viewer will not understand the data that it's getting, because it expects the linear array of bytes to have some structure, and this structure is internal to that file, but this is completely oblivious to the operating system. Okay, a directory has also two properties. It contains a list, okay, which is basically a list of user readable name and low level names pairs. So a directory, since a directory stores multiple files, it needs to store the mapping between the inode numbers that are the low level names and the high level names that basically I give to my files. That's the first thing. Also, a directory will have also its own number, so it will again have an inode number. So for example, let us say that there's a file with low level number of 10, an inode number of 10, and it is referred to the user by the user as foo.txt or foo only. Okay, the directory that foo resides in thus would have an entry of foo and 10. Actually, this is a bad example because foo in this tree actually has like a file in it. So foo is actually here a directory. So foo is a directory and you have bar.txt. So let's say that foo, the user readable name of the file is bar, basically .txt. So you have the directory tree where each entry in the directory refers to either files or directories. And by placing directories basically within each other, you are able to build your own directory tree, your own mental view of how your computer should be organized or disorganized, for basically depending on what kind of person you are, right? So you'll build a directory tree, and in Linux the directory tree starts with slash, which is basically the root directory. Okay, it's the mother of all folders. In Windows it's a bit different, because in Windows what you typically have is that you might have different directory trees based on what you have, like the C drive, the D drive, the E drive, and some people have like 10 partitions on their system, and their system is just a mess. So you will have, you can end up with multiple roots in that case, which is basically your drives. And when you're going from one level to the other, so when you're going, so you're on the root drive, on your root directory, and you want to go to bar.txt, you will typically say slash bar slash foo slash bar.txt, so you'll, or backslash, so you will have something that basically separates, that basically tells that I'm going from level 1 to level 2 to level 3 and so on. Okay, and the absolute path, the concept of the absolute path is basically from where you start, when you start basically from the root and go all the way to the directory that you want to go to, or the file that you want to go to. So naming is quite important, because everything in Linux, for example, is a file, as we said. So which basically means that if you end up with like dumb names, like a directory that's called A, and another directory that's called B, and the third one that's called C, and the fourth one that's called D, there's no way that you're going to know what A is and what B is and what C is and what D is if you go all the way to Z, right? I mean, you will forget. So you should basically pick names that make sense to your files and directories. File extensions is another concept that is, it's sort of a directive to the operating system to sort of know what file, what program can read that file. Okay, The first part is an arbitrary name because the first part of any file is whatever you gave it to that file. Uh, but having the extension does not mean that this is correct. As we said, I might be saving things into different formats. So it's just a convention basically. There's usually no enforcement of what file extensions you have. Windows does have some form of enforcement sometimes. Linux does that on very, very special occasions. But in general, no. You can just call your file whatever dot whatever. Actually, Linux is very, very relaxed when it comes to what you can name your file with. So it literally, you can name your file literally to whatever dot whatever. And then we have a file system interface that is implemented by file system. So you have, so we were talking about like the files and directories, which is basically the abstractions that we have in the file system, and now we are going to talk about the interface to create files and or directories. So this is, for example, the Linux way of creating a file. Okay, you have the open system call that takes a number of different flags that will create for you a file or a directory actually. Okay, so you have open. If foo does not exist, then you're creating foo, and if you are basically you can add a few flags to this. So you o create, o underscore create, o read only, o underscore truncate. So if the file exists, truncate it to a size of 0 bytes, which basically means that if you find foo, if foo is present, then please overwrite it and empty it. Okay, so by giving these flags, you're basically giving the operating system or the file system directions to create or open or read from a file. And then there's like the user, the last two flags is that user is enabled to read and user is enabled to write. Okay, so basically set the file readable by the owner and set the file writable by the owner. One important aspect of open is what it returns. It returns basically a file descriptor. A file descriptor, as we already discussed, is just an integer. It's private, purposes, and is used in Unix systems to access files. So a file descriptor is just something that points to the file. Once a file is open, use the file descriptor to read or write the file, assuming you have the permission to do so. So the file descriptor is sort of tells you which file you're open. And this way, file descriptor is more of a capability. It's basically something opaque that gives you the power to perform certain operations.